Okay. So last time we started studying the Picard group. Of isomorphism classes of invertible sheaves on X. And we had two, so to say, explicit, well, maybe you don't find it very explicit, but maybe better than nothing, incarnations. One was via invertible sheaves of ideals. So again, we need to consider invertible sheaves, but these invertible sheaves are realized as subsheaves inside this big constant sheaf of rational functions like this. And second was via the quotient group of divisors. This was the notation, right? D of X, modulo principal divisors. And here, the group of divisors was just formal linear combinations of subvarieties of codimension 1. And this made sense. So these are so-called André Weil divisors. And it made sense only if all the local rings were UFD. Okay, and now we will continue with this. So namely, we are going to prove, well, we are proving that one can associate to each divisor D an invertible sheaf of ideals probably we did not have we did not introduce any notation for this. Yeah, so it was O of D. So it's inside this big quasi-coherent sheaf of rational functions. So I want to associate it in the following way, so that O of D1 minus D2 is O of D, so to say, well, say times O of d1 over d2 inverse. Okay, and one
минус 1.
Inverse. Well, we are inside of this bigger quasi-coherent sheaf of invertible functions. So you just take inverse in this sense. So O of d2 inverse is the set of all rational functions such that f times O of d2 lies in OX. Okay. I think welcome. And now another normalization is that the constant function 1 lies in O of d if this d is effective. That is, d is some linear combination of irreducible divisors, but all the coefficients are positive integers. Okay, so I guess we stopped approximately here last time, and now let's go on. So maybe let me somehow announce before I prove this formally. Let me announce how does it work. So we know that maybe from the home assignment we know that the invertible sheaves are the same as line bundles. So L will be an invertible sheaf. The same as line bundles. So we will even denote it by the same letter L calligraphic over X. And now you see locally it's one-dimensional, well, free OX module of rank 1. So locally it's isomorphic to OX, and then locally it does have a section just given by 1, right? So as a local section, and then globally S is a rational section. With zeros and poles at some divisors, di with multiplicities say ai as above, and then what we want to achieve by this by the above construction that is not worked out yet, but we will in a moment work it out. So L will be just O of D, where D will be this sum of AI di. Okay, so this correspondence somehow measures the zeros and poles of rational sections. Yeah, and if I change my section, then what happens? S prime. We have S prime over S is a rational function. Okay, so it means that the difference d prime minus d is the divisor of this rational function this means that it's a principal divisor. Okay, and hence we have a well-defined correspondence between line bundles and isomorphism classes of line bundles and divisors modulo principal divisors. Okay, so this way we obtain the correspondence from Picard group of X, isomorphism between divisors of X modulo principal divisors. Okay, so that's how it works. And maybe conversely, given a divisor, T, we associate an invertible sheaf of ideals O of D inside K of X, the sheaf of rational functions. So these are all the rational functions with poles of degree at most AI along DI. And this is in some generalized sense. So it means that if AI is positive and regular along DI, if AI is non-positive with zeros of order at least negative AI, when AI is negative. Okay, so this is the definition of O of D. There's some sheaf of ideals, and this will be an invertible sheaf of ideals. Okay, so now this was sort of announcement, and now let's do this formally. So what I claim first of all is that given an ideal, sorry, given a divisor D, maybe, and again, no, I apologize. A subvariety D in X of codimension 1, its sheaf of ideals JD inside OX is invertible. Okay, and for this we certainly need this UFD property, unique factorization domain for each local ring, for the local ring of any point, we need this property. We'll see this in a moment. Why do we need this? So let's prove this for first play. Well, so let's consider this this ideal locally. So let's consider its stock or germ. At a point x inside this subvariety of codimension 1, or also divisor inside x, and we get j d x small, and now inside let's take some element, local function that is irreducible. Right, so we have this unique factorization domain property, so we can take any element. Now we can decompose it into the product of prime elements, and let's take one of those prime elements. Okay, then it is an element of the local ring, so it is defined in some open neighborhood of this small x, and let's replace our big variety capital X by this small neighborhood. It is regular on a neighborhood like this. So we replace X by U and assume F is regular everywhere. Okay, and now let's consider the zero divisor of this F. So the subset F equals 0. It certainly contains this initial codimension 1 subvariety, but maybe something else. Some other components of codimension 1, and they all combine into what I call C. C is the union of all the other irreducible components of F equals 0. All the other, I mean, not D. Okay, so now find another regular function. G on X such that G vanishes on C, but G does not vanish on D. It's possible just by the definition of irreducible components. So the C is closed, so it can be cut out by some equation. Okay, and now let say H be a function on X or on U, vanishing.
Вы уже воспользовались, что вот это UFD область?
Well, not yet, really, not yet, but we'll use it in a moment. Okay, right away. So let's take a function vanishing on this component D, and then if we take the product H times G, then it vanishes on the zero set of F, right? And by the Nullstellensatz some power of this guy is divisible by F. F divides H times G to some power. Okay, but now again let's return to our local ring or X that is UFD, and then we see by this UFD property that F divides H times G, but certainly if F does not divide G, right, because of their zero sets. And hence, by the UFD property, F divides H. Okay, so F is a generator of our ideal JD in a neighborhood of X, and that's what we wanted to prove. We wanted to prove that this ideal sheaf is locally free of rank 1, right? So it means that JD is locally isomorphic to OX, namely the generator 1 of OX goes to the generator F of our ideal. Okay, so we proved that JD is locally isomorphic to OX. That is, JD is invertible. Okay, and this was some big part of the proof, but only 1/2 of what we need, but still very important 1/2. And now let me give an example, or maybe rather counterexample. When O of D is not invertible for a singular X without UFD property. But I guess some people know this counterexample, so maybe somebody can suggest something. I mean, you don't have to guess my own counterexample. You can suggest your own counterexample. Anybody volunteering? No? Well, okay, then let me go on with my favorite counterexample. So X will be a hypersurface, three-dimensional hypersurface in A4, cut out by a single equation, namely AB equals CD, just a singular quadric. And it's three-dimensional, so a divisor D will be two-dimensional, and it will be given by, maybe now somebody can suggest this bad divisor.
Maybe A equal to 0?
A equal to 0. It's fine, but it's good, you see, because it's cut out by just one equation. So by the very definition, O of D will be an invertible sheaf generated by this very equation, A equals 0, right? So we need something worse than that.
Okay, then A equal to 0 and C equal to 0.
Right, that's it. That's it. A equals 0 equals C. It's, you see, it's still two-dimensional. When I suggested A equals 0, it had two irreducible components. One that, another one where D is equal to 0, right? But this is just isomorphic to A2. Nothing bad about this divisor in particular. But why is it bad? Why is it not locally given by one equation? I mean, it is explicitly given by two equations, but still maybe there is a way to rewrite it somehow in different coordinates as given by just one equation. So what is bad about this divisor? How do we see it's bad? How do we prove it's bad? Any suggestions? Well, then let's consider another one. Let's consider D prime that is given by B equals 0 equals D. Okay, it's also a divisor isomorphic to another plane like this. And now what's fishy about those two divisors? What's wrong with them? Yes?
They intersect in one point.
Right, absolutely. The intersection of D and D prime is just 1 point. 0 point, the origin. And what is bad about this? So these are divisors. They have codimension 1. And we would expect that the intersection would have codimension 2, right? That the codimensions would add up. And this is not what happens. Somehow the codimensional intersection is too big. And if you remember, some 2 months ago, we had the principal divisor theorem, which claimed that if you cut something by an equation of just given by one function, then the dimension drops just by 1. Maybe you remember. And here dimension drops by 2, so it cannot be locally given by just one function. So if D or D prime were locally, namely around this point, around the origin, cut out just by one equation, then the dimension of their intersection would be at least 1. Okay, so this is the contradiction, and it proves that neither D nor D prime can be cut out by one equation. You do really need both of those, A equals 0 and C equals 0, B equals 0 and D equals 0. Okay, so you see this, you do really need some regularity condition like UFD, and in this case it fails. Okay, so we proved
смысле сингулярно?
well,
В каком смысле X сингулярно?
we will have some definition of smooth varieties maybe next time, but I hope that in your usual geometric, maybe differential geometric intuition, there is no problem about this. That you know, actually you do know what it means.
Ну, в этом
Regular
смысле
or
понятно.
singular. Oh, yeah, that's all. Fine. So now let's prove the second claim. So the converse claim. Given an invertible ideal, well, fractional ideal, say J, but maybe not fractional, maybe just a regular ideal like this. We want to show that there is a divisor D such that, but maybe I should say an effective divisor and effective means that all the coefficients of our linear combination, when we write it down as the combination of irreducible codimension 1 subvarieties, these all coefficients are non-negative, such that J is OX of negative D. Okay, and let's prove this. So first of all, we note that OX itself is O of D for the trivial zero divisor. Okay, so these are just regular functions. So all their poles have degree 0. Okay, and now let's proceed by induction.
Извините, а верно ли, что OX от минус D это то же самое, что OX D в минус первой степени?
Absolutely, yes. But for effective divisors, OX of negative D is a subsheaf of regular functions of the structure sheaf. But OX of D is allowed to have poles. So it contains. Yeah? Let me write it somewhere here. O of negative D is contained in the structure sheaf. That is in turn contained in O of D. Okay, for effective divisor D. Right? So O of negative D are regular functions with some conditions on their zeros. Yeah, they're required to have zeros along this divisor D. But O of D are rational functions with some restrictions on their poles. So they must have poles of order not more than A sub I. Okay, so we proceed by induction. So how to say it? By inclusion. So we assume that our claim is proved by all the ideal sheaves J prime that contain our J and that are contained in the structure sheaf. Okay, so we know it for the structure sheaf itself. We want to prove it for J, but we can assume that it's known for all the bigger J prime. Okay, and we must find this some candidate.
База какая индукция? База какая индукция?
OX. We know it for OX. This is the base of our induction. The structure sheaf itself. Okay. And we must produce somehow this D, some candidate for D. So what will be our candidate for D? Can anybody suggest a candidate for D.
Maybe we take all the divisors corresponding to G prime, and then we take maximal.
No. Somehow we'll use this induction assumption in the proof below, but first we have to explicitly produce this D.
Maybe
out from
base point.
blue. Yes, so the D is just the support of well, its ideal sheaf is just J, right? Is the closed subvariety of X with ideal sheaf J. Yeah, so that's what we did in the first part of our proof, right? Given an ideal, we produce. Sorry, given a divisor, we produced the ideal sheaf from it, and now we're going back. So we just use the same procedure. So in other words, D is just the support of the quotient sheaf or X modulo this divisor, right? Because we somehow want that OD is just the quotient of OX modulo this divisor, this ideal. Okay, so we define our D. Now we have to, first of all, we have to check that it has really codimension 1. Yeah, because it could be just a point or whatever, some abstract closed subvariety. So why does it have codimension 1? Well, any suggestions? Well, in fact, we in a sense already discussed this, but let me repeat this.
Principal ideal.
Yes. Pardon me. Say it again.
Principal ideal theorem.
Absolutely, yes, absolutely. Because you know that locally this J it is an invertible ideal, so it's isomorphic to O. OX. So here we have 1. Here we have F generator. Okay. So locally J is generated by just one regular function F. And so this D is given by the zeros of this function F. But for one function F, by the principal ideal theorem, as Sergey mentioned, its codimension is exactly 1. Okay. The zero divisor of F has codimension 1. Okay, so we're in a good shape. We know that this D, well, it's a union of components, but each component that does have codimension exactly 1. So let's choose just one component. Say E inside this the zero set D, and consider its ideal sheaf, say J prime, that is equal to, or maybe let's do somewhat differently. Let's take our initial ideal J and now multiply it by OX of E. Okay, I mean, you can multiply ideals, yeah, in this sense. You multiply them. So I allow poles of order 1 along this component, right? That's our OX of E. So when you multiply it, these order 1 poles will cancel out the zeros along E, and so you see that this is still inside OX, but on the other hand, it contains our J, right?
Еще раз
Because
можете сказать, почему оно содержит J?
just because you know that OX is contained in OX of E, right? So OX are regular functions, OX of E are functions with possible poles of order not more than 1 along this component E. Okay, so when you just multiply this containment by J, you obtain this. But on you obtain this left containment. The right containment is clear just by the definition of J. Okay, so now by the induction assumption, we know that J prime is already of the good sort, right? By our induction assumption, J prime is OX of negative D prime, and hence J is OX of negative D prime minus E. And there we are. So we proved what we wanted for, sorry, for the sheaves of ideals J inside OX, but now we want to prove this for arbitrary fractional ideals, right? So for a fractional ideal, J inside this big sheaf of rational functions, we just decompose it into the product of two things. One is a regular ideal, and another one is inverse to another regular ideal. So we take J1 is the intersection of J with OX. So it's contained in OX, so by definition it's regular. And we know that it's eigeninvertible. By the unique factorization property. Yeah, just locally, because locally this J is generated by a single element, a single rational function f, and this rational function has a numerator and denominator. Now this J1 will be generated by the numerator, and then we know that it's invertible, and also we know that J1 times J inverse is also invertible. And it's also contained in OX, and so we know for both of them that they're associated to the ideals. And finally, J itself is the product of J1 times J1 J inverse inverse. Okay, and all of them are associated to ID to the divisors. Hence, J is O of so to say D1 minus D1 minus or maybe like this, yeah. That's it. So we proved our big theorem, and now we can derive some immediate and useful corollaries, applications. So first of all, as I promised, the Picard group of the affine space is 0. Why? Because we know that any invertible ideal is associated to a divisor, and again, this divisor is the difference of two effective divisors. Any J is J of D. Just because the polynomial ring is unique factorization domain, and any localization of it is also unique factorization domain, so the previous theorem applies. And we know that any invertible divisor is of this form, and D is the difference of D1 minus D2, where both D1 and D2 are effective. But then we know that any effective divisor, maybe let's say irreducible to be on the safe side, divisor in the affine space is the 0 divisor of a polynomial, regular function on this space. So any divisor is principal, and hence the group of divisors modulo principal is just 0. Okay, and that's what we wanted to prove. Okay, the second application is for projective space. And now it's the integers, namely the set of all line bundles or invertible sheaves, O of n integer. So why this is so? Again, because any divisor is the difference of two effective divisors, and for an effective divisor, D of degree of degree n, so, sorry, maybe I should say it in another way. Sorry. So maybe given given an effective divisor, there is homogeneous degree n polynomial, capital F, such that this D is cut out by the equation F equals 0. Okay, that this we proved some time ago. Essentially, just the same as before. We consider the cone over this divisor. It lies in the affine space. In the affine space, we already know this. And now we only impose this additional homogeneity property. Nothing new. Okay. So then again, by local consideration, there is a morphism from OPD of negative n to OPD, the structure sheaf. And this morphism is just multiplication by F. Yeah, because well, locally you consider some homogeneous functions of some degrees, and multiplication by F raises degree by n exactly. So it makes sense. And I claim that the image of this, first of all, it's an embedding. Yeah, because there are no zero divisors. Yeah, F times something is never zero. And the image of this embedding is exactly the ideal sheaf OPD of negative D. Okay, because just what do you want to get? We want to get the regular, well, local regular functions locally divisible by F. That's what you just tautologically get. Okay, so we somehow classified all the ideal sheaves of divisors. Yeah, they are absolutely isomorphic to OPD of negative n, where n is the degree. So any ideal sheaf of an effective divisor of degree n is well, abstractly isomorphic to OPD of negative n. Okay, I mean, when I say abstractly, I mean that just as invertible sheaves, they're isomorphic. There are many actual embeddings of these sheaves into the structure sheaf of regular functions and into this big sheaf of rational functions. But just as sheaf of OX modules, they're isomorphic to one and the same OPD of negative n. And that's it. This implies that there is a surjection from the integers to the Picard group of the projective space. So everything is defined just by its degree. And now we only have to prove that there is no kernel. I mean, it remains to check that PD of n is isomorphic to O PD of L, whatever, if and only if n equals L. Yeah, and well, say let's suppose that n is bigger than L, and then let's take the ratio O PD of n tensor O PD of L inverse is isomorphic to O PD of n minus L, and I claim that this is not isomorphic to OPD. Why it is not isomorphic? Any suggestions?
Maybe the corresponding line bundles, we can look at them, and we proved that they have different global sections.
Right, absolutely, yes, because so they are distinguished by their global sections. The global sections of the structure sheaf are just constants. You know this, but the global sections of O and minus L, they are just symmetric n minus L power of a certain V, yeah, or maybe V star, where PD is the projectivization of V. Okay.
It could be zero, but
yeah.
then we take it could be zero, but then we take the dual.
What could be zero?
The global sections of if n.
Right, but for this reason, I assume that n is bigger than L.
Okay.
But your argument is perfect, absolutely. It's even easier in the opposite direction, yeah, because just zero. Anyway, it's not K. So I mean, it's not the our base field.
Yeah, I see.
So, okay, so there we are. We proved that all those line bundles are really not isomorphic, because if they were isomorphic, their ratio would be just structure sheaf, but it's not. Okay, so there we are. We classified all the line bundles or invertible sheaves on the projective space, and that's a big success. And now let's move towards the classification of line bundles or invertible sheaves on the other varieties. And to this end, we will need the operation of pullback. Of line bundles or invertible sheaves. Since we don't distinguish really between those two notions. And for the pullback, again, I think everybody knows this from the differential geometric intuition or whatever. So if we have a morphism like this, and over Y we have some vector bundle or line bundle V, then we can pull it back here and denote it F upper star V over X. And well, so I hope you remember from the home assignment a few times ago, what is a vector bundle? A vector bundle is some other algebraic varieties equipped with a projection to the base, so that all the fibers are vector spaces, and somehow it's locally trivial, but the gluing of various trivializations respect this vector space structure. So the gluing functions are linear in the fibers. Okay, but anyway, it's just another algebraic variety. And then by definition, this F, the pullback of V, by definition, is the Cartesian product X over Y with V. Okay, and what is this? This is subvariety in the direct product, X times V. But you see, both X project, well, maps into Y, and V projects onto Y. Maybe like this. So we have a map from X times V into Y times Y. Namely, it's P along the second factor and F along the first factor. And we have this diagonal embedding of Y into its square. Okay, and the Cartesian product, by definition, is the pre-image of the diagonal. Okay, and I'm sure everybody heard this many times and knows this. So I'm saying nothing new, that you can pull back vector bundles. Okay, now we know that there is an equivalent language to speak of vector bundles, namely the language of locally free OX modules or OY modules. So there must be some way to pull back the locally free OY modules. And indeed, there is the corresponding operation. Sorry. That is also denoted F upper star on the sheaves of OY modules. Namely, it will go from, say, quasi-coherent sheaves of Y modules to the quasi-coherent sheaves of X modules. And if you remember, we already had some sort of pullback for sheaves, but it was disregarding the structure of OX or OY modules, and it was just F inverse, so to say, yeah, from sheaves on Y to sheaves on X. But without, once again, without any reference to the structure of modules over the structural sheaf of Y or X. So that's not what we want. If you just pull back a sheaf like this, you will not get anything meaningful. For example, if Y is just a point, then F inverse, say, OY, so OY will be just the constant sheaf, the K, yeah, of our base field K, the constant sheaf with coefficients in K. And then its pullback will be again a constant sheaf. Say K underline on X. So it's not a sheaf of OX modules. So it's not what we want. Okay, we want something else. So we have to modify this notion of F inverse. And modification is very, very easy, and somehow it calls for such modification. So F inverse is replaced by F upper star. And what is it? You see, let's take the pullback of the structure sheaf OY. Okay, then as we just argued, it's a bad sheaf on X, but still this bad sheaf it's too small, so to say. It's too constant, but still it acts on the interesting structure sheaf on X. Yeah, on OX. Right, because OX is the sheaf of all regular functions on X, and now the pullback F inverse OY is the sheaf of functions that are constant along the fibers. Okay, these are not very interesting functions, but still among all the interesting functions there are such not very interesting functions, and they act on everything. Okay, and then the definition is F upper star for any sheaf of OY modules, by definition, is we pull back in this stupid way, so to say. Okay, now it is acted upon by the pullback of OY, the stupid pullback of OY. On the other hand, the stupid pullback of OY acts on OX. Okay, so we can form this tensor product, and on this tensor product OX just by construction, by definition. So it's a sheaf of OX modules. Okay, so that's the definition, and you can check, for example, that it works for the vector bundles. It matches the pullback of vector bundles. And it has some nice properties. Let me list those basic properties. So first of all, it does take quasi-coherent sheaves to quasi-coherent sheaves. And in fact, the second observation is that for the push forward already has this property. You don't need to do anything. The abstract push forward for OX modules automatically lands in the category of OY modules. What? To OY. Okay, and these two functors are adjoint. So F upper star is left adjoint to F lower star. So F lower star is right adjoint to F upper star. And then on the general grounds, F lower star is left exact, and F upper star is right exact.
Образа надо брать пучковизацию? Для образа надо брать пучковизацию?
For the direct image or for the pullback?
Прямой образ.
For push forward, just usual push forward. You had some home assignment about this, and nothing changes. Just literally the push forward for sheaf as is defined there.
Хорошо,
Yeah.
спасибо.
Okay, and maybe let's discuss a little bit. So you know that global sections are only left. I mean, the push forward, at least in the case of map F going to the point, is just global sections. And you know that global sections are left exact, but not necessarily right exact, or only for flabby sheaves. We discussed this. But about this pullback, can you give an example when it is only right exact, but not left exact? Let's discuss such an example. Is not left exact. Yeah, in fact, we already discussed this a couple of times ago, so let's just recall it. So can anyone give an example?
Maybe fibers?
Yeah, just closed embeddings, absolutely right. Say embedding X like this. Okay, then F upper star will just taking fiber. X. So in other words, F upper star F, I mean, for a quasi-coherent sheaf is F tensor over OX with just the skyscraper sheaf at our point. Okay, and this is clearly not necessarily left exact. Okay, so that's it, and maybe we'll have some time for projective morphisms. So description of morphisms F from X to Dn in terms of invertible sheaves on X. Okay, so this is something very simple-minded on the one hand, and on the other hand, it's very important. So I don't know how to stress this point, but it's a very ubiquitous and important construction. So given such a morphism F, we associate to it just the pullback of this invertible sheaf O of 1, and there we are. But maybe let's somehow muse about it a little bit more. So we know that the sections of O of 1 are just the linear functions, and let's pick these particular linear functions, kx1 plus so on plus k, maybe kx0 plus kxn. Okay, so these are just standard coordinates. Okay, so they form a base of the global sections, and our line bundle is globally generated. So we have a morphism from the trivial line bundle or the structure sheaf itself, OPn to the power n plus 1 onto OPn of 1, namely the I summoned is multiplied by xi, the corresponding coordinate. Okay, and this is clearly surjection because we only have to check this on fibers, and we have to, on fibers we have to check that those coordinates from x0 to xn never vanish simultaneously. Certainly, they do never vanish simultaneously. It is surjective. Since x0 and so on, xn have no common zeros on P. Okay, and then the same property continues to hold for the pullback. Now, the pullback of xi is a section, a global section. Say Si of the pullback of 1 on x, right? We started from morphism, from projective morphism, from x to Pn, and now we can pull back everything to x. We pulled back this O of 1 invertible sheaf to x. We're pulling back the sections, and everything works on there, and we have the corresponding morphism, OX to the power n plus 1. Again, it surjects onto the pullback of O1, and again on the ith summoned, it's multiplication by Si.
Mishan, may I ask a question?
Yes.
When you write that I summoned is multiplied by xi, xi is not a global function on projective space. It's something else, and I do understand this on global sections, but maybe, to define.
Yeah, that's what I mean exactly. Yeah, it's a global. So a morphism from O to something is a global section. So home from OX to whatever is just global sections of X with coefficients in F. Okay.
Okay.
So that's what I mean here. Okay. So is it okay? Yeah. Fine. So once again, if we fix the standard coordinates on our vector space, whose projectivization is projective space, then we can pull them back to X, and there we will obtain some sections of the pullback of this O of 1, namely such sections that generate this pullback at each point, so generated globally. Okay, and maybe I will need a couple more minutes if you don't mind. Then let me state this proposition. And it's very, very simple, but very important once again. Somehow it is converse to what we just constructed. So given an invertible sheaf L on X and global sections S0 and so on through Sn, generating, generating L. So it means that from OX to the power n+1 to L, there is a surjection given by S0 through Sn, like this. So given all this stuff, there is a morphism F from X to Pn, such that the above L is just the pullback of O1, and all those SIs are just pullbacks of the standard sections. Okay, and the proof is, as I said, very simple, immediate. Just we glue it from the standard charts on the projective space. Namely, we set the basic open subspace, the ones where the sections that do not vanish. Such that Si of X is not 0. These are opens. And now we construct a morphism Fi from Di to a n, but maybe not number I. Just the standard charts on the project space. Yeah, and what is this morphism? It is just tautological. Say, Vanya, Ukrainians, can you tell me what is this morphism? By chance. And if not, maybe Yitya, who can you tell me what is this tautological morphism in this open chart? Maybe Wei Chen, can you tell me?
I'll have a try.
Yes, yes.
So the for every coordinate in a I and let's say xi,
Yes.
xi is given by si quotient by s. No, sj quotient by si.
Yes, absolutely. Yes. Sj of x over si of x, but here j is not equal to I. Okay, and since Si of x is not 0 on this open subset, this ratio is regular. Okay. On Di. So thank you, Weichan. That's absolutely right. And they glue together to the desired morphism F from X, that is union of di to Pn, that is union of those charts, standard charts. That's it. Well, so maybe let me stop here, or maybe just let me say one word of terminology. Such an invertible sheaf L is called very ample if F from X to Pn is a closed embedding. Okay, so certainly you could consider, say, a trivial line bundle, yeah, and then it would correspond to a map from X to a point in projective space, and that's not very interesting. But we're interested in the opposite case, when this line bundle is as non-trivial as possible. So when this map from X to Pn is an embedding, it does not glue anything at all, and that's called very ample. So we'll consider the examples of this next time, and then the whole next year. So let me stop here and ask for questions.
Вот в этой формуле для отображения FI нужно, получается, выбрать какую-то тривиализацию L?
No, because as we discussed already in the beginning of today's class, the ratio of two sections is always a rational function. Yeah, a section, well, to think of section as a function, you need to choose a trivialization. But a ratio of two sections is canonically a function. You don't need any choice.
Потому что они линейные на слоях.
Because the line bundle, yeah. So there, at any point, the ratio of two sections is just a number.
Хорошо,
Well-defined
спасибо.
number.
Misha, maybe we want to also to say that that there are no points in X such that all the sections vanishes simultaneously.
Didn't I say this? Sorry. No, I said, you see here, generating L. So that's what you say. Yeah, I mean that this morphism from this trivial vector bundle to L is surjective. This exactly means that the sections never vanish simultaneously. That's just what you say.
Yeah, but okay, yeah, I see. Thank you.
Welcome.
Извините, я немножко запутался.
Да.
Вот кольцо регулярных функций от минус d по определению это что?
O of negative d is a subsheaf of the structure sheaf formed by those functions that vanish at divisor d with appropriate multiplicities. They are everywhere regular, and they must vanish at d, well, with multiplicities prescribed by the multiplicities of this divisor.
Спасибо.
Okay, so if there are no more questions, I am saving the notes. I'm stopping the recording.